All right, hey everyone, what's up? Welcome to week 37 of Chill Kernel Hacking for Fun. Let me get the music going actually. There we go. All right, I'm just gonna do a quick test in the chat. Yeah, so today it's another exciting day of kernel debugging. I have been working on this very difficult collection of bugs for a while now, and I'm making a lot of progress on one of them. Also, as a quick note to the viewer, if you last watched week 36, then actually what I'm doing right now is not immediately going to make sense to you, because I actually filmed another stream just beforehand, and I'm going to release that one in 1 week from now as a pre-recorded stream. So there's going to be a little bit of a continuity gap. Yeah. Oh man, I just realized my camera is a bit low on battery also. That's unfortunate. I might have to switch to my front view today. Yeah, I think I might need to switch cameras. Actually, my camera's gonna die. I'm just gonna take a moment to get that set up. Give me 1 second, I'll be right back with the switched camera. Yo, Reza, welcome. I'll answer that in 1 second. I'm just finishing up switching my camera. Okay, video capture device. All right, let's get this thing situated. Okay, looking good, looking all right. Yeah, what should I learn to understand what you're doing? There's a couple main things. I'm going to link you to my resources. Basically, C programming, operating systems, and a bit of assembly are the main areas that are relevant for me. Yo, what's up, Ujwal? Welcome. All right, so let me just adjust this a little bit. So yeah, today we're diving into another adventure of kernel debugging, and I'm debugging some pretty intense problems right now. Right. I am currently debugging a crash that happens when the kernel kind of destroys a process, and kind of a process exits and it's time to destroy the process. Currently, the kernel is crashing. And I am getting pretty close to it. I made a lot of progress last week in week 36, and I'm building on that now. I guess I made a lot of progress in week 36 and week 38, which will be coming next week. And I'm building on that now to debug this crash. Thanks. And what does job market look like for these skills? I would say it's a pretty good job market. Yeah, I mean, these are pretty rare skills, and the entirety of the computing industry rests on stuff like this. You can find a lot of jobs in the hardware industry, in particular, on embedded systems often require a bit more. Although to be clear, like actually doing legit kernel development is like kind of rare, to be honest. I don't do that in my job. You know, there are people that work on the Linux kernel, but most of them are not doing the kind of stuff that I'm showing in this video. There are relatively few jobs if you're looking to actually do hardcore stuff like this. Also, the information security industry has a lot of good low-level work too. And this software is called Miro. That's what I like to use. But yeah, so today we're debugging this like kind of wild kernel crash related to the stacks. And there was this problem where in the code path for destroying a process, we have this pointer to the process. It's called an environment here. And we switch the CR3 virtual memory. And then as soon as we do that, we get a null pointer dereference type of crash when this E thing becomes null. And the reason the reason for that is because we switched the CR3, which changed the virtual memory mappings, which my theory is that it changed the stack to point to a bunch of zeros in memory, to like effectively uninitialized memory. And I'm building up my understanding in order to fix this bug, which is what I've been doing. And that's kind of what I've been doing here. So I've been doing some research and kind of learning, refining my understanding of how the stack actually works with the kernel and the various transitions that happen. Hey, Dr. Deathvolt. Hello, what's up? And I basically, so all the work that I'm showing in this part of the board, that's what will be in, I'm uploading a pre-recorded stream next week in 38, so you can see me mapping this out next week in week 38. But basically, the high-level process is one, we boot up and we start running on this thing called the boot stack, which is just a very basic region of memory. We do that for quote-unquote a long time, which I kind of want to debug further. At some point, we enter user space and drop into the user space stack via the trap frame. And we switch the stack to U stack top. And then eventually an interrupt or exception happens, and we switch back onto a kernel stack. But this time we switch to the K stack region rather than the boot stack. The boot stack is this thing. And it's like boot stack vAdder basically. And then the K stack is a separate region. Yeah. So what I'm going to do now is I want to confirm that my current understanding is that we actually stay here for a very long time. We set up this K stack region, which is kind of meant to be the kernel stack, but currently I don't think we're actually using it really. So I think we stay here for a very long time. And the way I'm going to confirm this is I'm going to probably find the moment that we enter user space and then check out like right before we drop into user space, what does the stack look like? My prediction is that it's going to be a boot stack vAdder, not a K stack vAdder. So let's just take a look. Okay, quit this. Ooh, wow, okay. No, okay. I want to debug, and what I want to do is I want to debug at env run, basically. Env run is where we kind of start to drop into user space. And I'm gonna break there. And then now I'm going to look at the stack pointer. And yeah, and this is exactly what I expect. So this shows, this is ESP at env run time. We are still using boot stack vAdder for the stack. We haven't migrated to K stack yet, even though the memory is mapped. So that helps refine this understanding. Yeah, what's up, Jay? Hello, friend. Is that a GDB interface? Yeah, I'm using GDB for debugging. Yep, thanks. Right. And so it's a little bit confusing because we do have this region, but it's actually like just not used. Yeah. How you plan your projects, like for example, you're developing a kernel, what's your first step and how to execute the whole project. So just for context, I'm not really, all I'm doing is following this coursework on this MIT class. I'm not really doing a lot of planning. I'm just following the coursework here. Yeah. Okay, so basically, yeah, so it confirmed that we're still on the boot stack. What I am actually kind of interested in is, I want to go back to mem init, which is where we set up virtual memory. Here, we're setting up, here's where we actually map the stack, the K stack region, which points at the boot stack at the moment. But then right after, yeah, and then we load, so basically the like general flow is we boot up, we have this really, so I'll try to write this down. So this one, we boot up super basic virtual memory entry page dir stack points at boot stack. 2, we set up production virtual memory with K stack mapped, etc. That's step number 2. But the stack still points to boot stack. That's a little bit interesting and kind of confusing actually. But I don't think it's actually super important. Yeah, I'm a little bit shaky. I just know that eventually we do get to K-stack via interrupts and exceptions. Yeah. We never explicitly change ESP to point to K-stack. Yeah. But now this is interesting. So this, I'm still trying to kind of understand things. Yeah, what I kind of, what I kind of want to know is where the stack is before and after. Like where the stack is mapped to. So here we should be running in, so yeah, we definitely are running in K-stack, in the K-stack region. In both cases, but it's just, the question is where does it point to? And why? What is going on here that would change that? Although I think we're still running, was that Afnan? Yo, Afnan, what's up? No, it's like this is like my old camera view. My camera ran out of battery, unfortunately. My camera being like this like random phone I have, so I'm back to my normal webcam view for today. I always forget to charge like the camera, yeah, or the phone. So, road to 5K. We're getting there close. Yeah. Yeah, Afnan, you've been along for a lot of the ride. That's pretty cool. Thanks for joining for so long. Bro, something is better than my phone. Okay. Back to thinking about this though. I'm not. So I have some loose understanding that we're operating in one set of virtual memory here. We swap into a different one. Operating with user and virtual memory. 2, swap into kernel virtual memory. And then 3, the stack now is mapped differently. But the key point, but it's still mapped, just is zeros. The fact that we read zeros mean it is still mapped. What? Yeah. What? So I believe that's true. I think, yeah, we're operating. When the interrupt happens, it doesn't swap CR3, I believe. Okay. I think, okay. Random idea of the bug. I didn't modify env setup VM. That is still mapping kstack to the boot stack, but separately. Oops. Current pagedir, it has been changed to map kstack to per CPU stack 0 or whatever. I actually think that might be the problem. Yeah, I think that might be the problem. Why Miro? Because Miro's good. Miro's such a good tool. I can put screenshots, I can draw lines. It's very high performance. I like Miro a lot. So here's this thing. And I think it's a bug. Okay, I think this might be the bug. There's something like it. I guess okay, just my thoughts are kind of going every which way here. Yeah, but can you use screenshots in Excalidraw? for me, Miro is like the 10 IQ thing. It's just like so easy. Can you like just draw lines and stuff? But if that works for you, that's cool too. Yeah, what was I saying? Yeah, my thoughts are going kind of everywhere, but so going back to this, so I guess technically I was a bit confused at how we're using the ESP here in the boot stack when we have this region that's specifically created for the kernel stack. But it doesn't really matter because they both map to the same physical memory, so you can kind of use either one. And I guess as soon as there's an interrupt, we will reset to start running from here anyway. So it's not really a problem that we just continue to run on the boot stack. Yeah. Okay, that was just a random thought. But I have this suspicion, or rather, idea that this is actually kind of a problem. And yeah, because let me see if I can roughly map something out. So let's say we have the user, or actually wait a sec, no. Okay. So what do I want to do? I want to make a copy of this thing. Okay, so we have our virtual memory for the kernel that the kernel runs in and stuff. Then it's time to set up an environment. So we have user environment memory in lower memory, and we map like a ton of stuff. But we still map initialize the kernel virtual memory layout for environment E. Allocate and initialize the kernel portion of the new environment's address space, right? And so I have a bunch of code that runs over here, and I'm actually going to make this a bit bigger because to further illustrate the situation, I have the boot stack. Then I also have the per CPU stacks array. And this thing is huge. This is like very much not to scale, but you know, this is like large. It's stacks for 8 CPUs, etc. Whereas this is just a simple stack. And what I believe I'm doing is, oh, oops. So first, where did my code go? Okay, so first in pmap, okay. So we map here. We map the kernel, so we map the K stack to point to boot stack. So that's this arrow. Maybe I can make it a bit bigger too. That's this arrow. But then I call this function mem_init_mp, which does this thing that I think is kind of buggy, maybe, where I then call bootmap region to map so K stack, and then okay, yeah, no. Basically, I map it to point to PA, which is the per CPU K stack. So I'm basically just taking this arrow, and I believe I'm just pointing it here, actually. And this is setting up the this kernel virtual layout. But and that's pretty much it. I think I call that function, and then then we just kind of load that in and lock it in. But then later, it's time to create an environment. Oops, it's time to create an environment. And we call env create, and we call env alloc, which calls env setup VM. And here it's time to basically recreate a lot of this stuff for the env vadder space, env maybe virtual space. And it's time to recreate this, but unfortunately I copy and pasted the code. Which maybe is kind of unfortunate. Yeah, I mean, I'm experiencing just a lot of pain in debugging because of kind of poor program design and bad software engineering a little bit. All right, time to catch up on the chat. Yo, Lizard, what's up? Good to see you, man. Looking for an area in software development I can build and do nice stuff with few texts, but knowing them in depth. Hey, what's up, relaxing sounds? Hate web dev. Lots of similar texts and things to know. Not sure if kernel development lots of my interest. Must be game dev. I ain't gonna touch or even think about doing kernel dev because I can't even make a proper link list and see. Just start. Yeah, mostly don't even. Yeah, Dr. Deathful, I think that's good advice. Just start. When do you think it's too late to apply for an SE internship during the summer? I mean, I think it's like the ideal time to apply for internships, like a summer internship, is probably during, I mean, like maybe like January or so. Maybe even earlier sometimes, but like maybe like January is about a good time, or February. You could try even earlier, maybe. If you're applying to internships in like May or June, that's getting a little bit late. Yeah, it might be hard for a company to accommodate that so quickly, unless it's like a very agile startup that just can like immediately just hire you. Which course? What's up, Maz Munir? Here's the course. Yeah, embedded is pretty good. Yeah, I think, yeah. Honestly, I don't know if I can really even speak to that. I don't have enough experience with the industry. What's up, Zabriel? Yeah, I was in cybersecurity for a while. Yeah, about 6 years. Back to work. Okay, is this a bug? I think this is a bug. So let me go back to my illustration. So I copied and pasted all this code to set up set up all this stuff, like replicate what I did here over for the environment. But since I copied it and pasted the code, I didn't fix up this thing that points this K stack to boot stack still. Yeah, I think March can be okay. If you can, I mean, if you can be earlier, I think it would be nice. But I don't think March is too late. But it kind of depends on how competitive it is, also. Okay, so basically, what was happening is something along the lines of. Okay, so ESP is like the processor register, right? And I'm gonna make this line huge. Okay, so first ESP, we boot up, we're pointing here. We run here for a very long time until it's time to execute the first user space process, at which point we switch the stack to point somewhere into the user space memory, and user space gets going. And then we switch to then an interrupt happens, and we switch ESP to point to this K stack top, still within the N virtual space, and that is pointing way down here. And then we're running, and that's the context in which we are running. I'm going to copy this. And that's the context in which we're running here. We're at the beginning of this function, and we are doing, ESP is pointing here, our stack is pointing here, which points to boot stack. Then we do load CR3 for the kernel page dir, which engages this set of virtual memory mappings, which points at a totally separate region. And I believe that is the problem. Because a bunch of stuff got added here, and then we start to read from here, which is like all zeros. So actually, I think I have a decent understanding of this now, though, but I'm still not sure how to fix it. All right. Oh, my break timer. Let me get that going. I'm gonna take a 20-second break to stand up and stretch. I highly recommend you do that also. Be right back. Okay. So what do I do? What do I want this to look like? I think the clear is there. I mean, just thinking out loud, it's a big problem that these things point at different places. So I think I need to make them point at the same place. But this thing is actually a bunch of different stacks for all the different CPUs. So I'm actually pretty unsure what to do about that. One thing I just want to walk through is so the question is, why does it work? If I comment out this boot map region, if I comment out boot map region, there's no longer this kernel crash. This fixes it. Commenting out this line fixes it, and I just want to kind of make sure I understand why that's the case. So if I comment that, what does this do? So what part of the code is this? This is mem init mp. Come on. Mem init mp. This is the part of the code that resets this thing and makes it point here. So if I comment out that line, this thing still points here, which means, and this thing, the current state of the code, this thing points here. So that's why it works. I'm pretty sure. If I comment out that line, we just remain running on the boot stack and everything is totally fine. The problem is introduced when I try to update this thing to point to a per CPU kernel stack, but I don't change this. And the idea is to make everything look like this. Okay. I think I'm starting to get somewhere. So I think what I need to do, so the question, so what causes this? This is set up by the TSS in the interrupt descriptor table, and the TSS points to K stack. But actually, this part of exercise 4, so previously it used to always only ever point to K stack top. Yeah. Okay, now this is getting a little bit trickier. So we have actually like a couple kernel stacks. Let's imagine we're on a system with 2 CPUs. K stack 0. We're going to have 2 stack regions, and I mean this diagram is quickly getting pretty messy, but it's going to look something like this. I feel so silly making this crazy, stupidly complex diagram. Known, very thin dotted lines. So I'm just gonna move this into the middle. I don't know if I can do that actually. Okay, so basically, wow, need to make that smaller. K stack 0 fizz mem. And then this is going to be K stack 1 fizz mem. 0 points to the 0 thing, 1 points to the 1 memory. And so currently, like without this patch of code, anytime there is an interrupt on any CPU, ESP is going to get set. I guess I'm gonna move this over here. At any time on any interrupt on any CPU, ESP is going to get pointed at K stack 0, basically. And that is not okay, because if multiple CPUs have interrupts at the same time, they are going to trample all over each other, because they all are going to point at this exact same place and be pushing and stuff onto this part of the physical memory in like concurrently in a totally uncoordinated way. So what needs to happen is that we need to adjust the interrupt handling like logic to conditionally point at one of these stacks depending on the CPU. So if an interrupt so without the patch, any interrupt on like any CPU gets K stack 0. Not good. What we want is an interrupt on CPU 0 has the stack pointing at K stack 0, and an interrupt on CPU1 has the stack pointing at kstack1, which each get appropriately assigned. And that's what this patch does by man, yeah, it's a bit too complicated to like, kind of go into. I did this weeks ago, in like week maybe 32 or 33 or something. We get the CPU number and we compute a stack address to use and assign that into the task state for this CPU. Yep. And so each CPU is initialized to point to a specific place here, to point the stack to a particular region here if an interrupt happens on that CPU. Yeah, so I don't have that yet, but that's actually kind of important. So I think there's 3 components to this. Currently the 3 components are 1, the kernel code to set up kernel vert adder in mem init. 2, code to set up user, like process vert adder, or kernel portion of process vadder in env setup vm. And 3, code to make interrupts on CPU handled. And I think if we have all 3 of these things, we finally kind of reach a state of harmony and get things working. Okay, so that's eventually the goal, to get all of these things working in harmony. For the moment, I'm not actually using multiple CPUs though. I am only using 1 CPU. So I kind of don't need to worry about this thing. And basically, to get this working in harmony for a single CPU, all I need to do is fix this inconsistency where the stack 0 points here and stack 0 points somewhere else. So I could technically it would be a pretty simple change. I could just simply point this not at boot stack, but at per CPU stack 0 or something. What I'm actually a bit confused about though is how does this code need to change to support multi-core? Though, I think I need to map all of the kernels. I mean, yeah, I think I need to, let's see. I think I need to replicate actually this whole loop. Or maybe even call this function, although it's static. How do we handle the boot? Yeah. Okay, the answer. Now that I actually know the answer to this question, we handle the boot stack. Migrate when an interrupt happens and we formally reset ESP to K stack region. It's not a big deal. oops. Yeah, that's basically the answer. Okay. But yeah, I think I need to replicate all of this code in instead of VM in order to map all of these possible stacks into memory, because the process, like the environment can execute on various CPUs. Like the OS can schedule it to run on various CPUs, and it needs to be like an interrupt can happen on any of those CPUs, at which point we've set up the ESP thing, the TSS, to point ESP at like one of these places, and we'd better make sure that these are all mapped, basically. So the equivalent arrow, messy arrow, would be this. We had really better, so the CPU is going to point the stack at one of these places when an interrupt happens. We really need to make sure that any of these possible places are mapped, any possible one, because we don't know, because the process can move around on any CPU, therefore it can get an interrupt on any CPU, therefore ESP can point to any of the possible places during the lifetime of this thing, which means that all of them need to be mapped. And currently, and that's exactly what this loop does, and that's what I'm missing here, I think. Okay, that was actually kind of, I think, again, that's just my understanding here, but I actually think that's kind of sound, and I think I can actually finally move forward with doing something here. So I'm just going to map out what I'm going to do. So step 1, keep multi-core disabled. We're keeping multi-core. We're just trying to fix the null pointer deref crash. The hack to do so, comment out mem init mp, but that's not really a solution. We're just not doing the work. The real solution here is to fix env setup VM to not point k stack to boot stack, but rather point it to per CPU stack 0, specifically 0. And I think if we do that, if we do this, we should not see the null pointer deref. Because what this card means, fix env setup to not point kstack at boot stack, but rather at per CPU stack 0. What that means is make this arrow not point here at boot stack, make it point here, such that it is in harmony with this thing over here. And I think that will solve the crash. And then, okay, that'll solve the crash, but then we want to eventually then we want to get multi-core working. That would be a next step. Because this fix is not enough to get multi-core working. This is not enough to support multi-core. Oops. Caps lock. Okay. Multi-core, because only stack 0 is mapped still. We need to replicate the mem init mp loop and map all stacks into envs also, not just the first stack. And the interesting thing, yeah, what's up, Jimothy Sherwood? And the interesting thing, I don't remember ever being told anything about this. I've been mostly under the impression that the coursework is going to tell me what to do in order to avoid major problems like this. But this is not the first time that they just low-key, like, I have had this major issue that's taken me a super long time to debug, and they did not even give me a hint of something to do. I would maybe expect a small hint saying, hey, you know, remember to fix up your env set of VM to be consistent with the mem init function, but that is nowhere to be seen. So, right. So this would be the general plan. Step one, just get the fix enough to kind of get non-multi-core working, and then actually try to get multi-core working. But the big scary monster, what about the QEMU crash, is will the QEMU crash still reappear here though? I'm not sure. I think it might. But it's also maybe possible that actually fixing these issues might even fix the QEMU crash, although I am not so hopeful. But okay, well, let's get to work. Quick break to get some water, and we'll get going. Okay. So, step one. So we have, so what's a working sheet looking like? My is this a bug comment? My answer, which honestly we don't really need. Maybe I'll just screenshot this and save this in the Miro. Oh, 20-second break anyway. All right. 20 seconds, be right back. Yo, Ismail, what's up? I have your stream on the background. Thank you very much. I think we're getting there. I've constructed the most confusing mirror board in the world with all these crazy arrows, and I think we're getting there. All right, so let's run the plan. So, let's run the plan, guys. So step one, let's do this. Fix this to not point at KStack, to boot stack, but rather point it to per CPU stack 0. Okay, actually, step one, the real step one that I want to do is just show you all the bug before I even try to fix it. I'll just show you what it looks like. And to do that, I need to re-enable this. And then what we see is here. This is the bug. This E variable as a pointer, as the same pointer, and then it becomes a null. And then our assertion fails. Previously, it was actually crashing on the null pointer dereference, but I've since added an assertion. And so that's what the bug looks like. This assertion fails, and it fails at this point in 730. It fails at this point in the code, which is kind of what I was showing earlier. So this is like the crash. If we didn't have this assertion here, it would actually crash on this line when it attempts to dereference the E null pointer, like member, struct member thing. So that's what the bug looks like. Now it's time to do the fix. And here's what that's going to look like. But it's actually here. So it's actually going to be here. Right, so what did I say? Fix to not point at boot stack, but rather point at per CPU stack 0. So it's a super simple fix, but all that's going to look like is instead of doing boot stack, we're doing per CPU kstacks 0, and I think maybe even getting the address, the first one. That's it. With this change, we're pointing at, we're doing that movement of the arrow. We're no longer having this kstack 0 point at boot stack, we're pointing here. And that's it, that's literally it. Let's see what happens. I am hopeful that we're gonna run this, and we're not going to see this. What we are going to see is like the success screen, which looks something, I don't know, something like, I thought I took a screenshot of it somewhere. Okay, I don't see it. All right, whatever, let's just run it. Yes, that's it. That's the success screen. Success screen says no runnable environments in system. The pointer is valid in all cases. Sick. Okay. That worked. With the light blue. Okay. So phase 1, that thing actually did work. And yeah, that's pretty sick. Is this a bug? Yes, that's a bug. Time to fix the bug. I'm actually going to fix init mp. Previously they were inconsistent in where they mapped kstack region to. This caused a crash when env-free swapped, or not swapped, switched back to current page dir from the env page dir because the stack effectively got cleared out, zeroed out by this fixes the crash. Okay, that's actually pretty sick. I'm actually really excited about that because this has been I've spent probably over a month on this bug, by which I mean my 2 hours a week. So I spent a long time around this topic. So that's actually really nice. Yeah, I think I'm gonna call that a win. Call it a W. Okay. Now we can move on to the next one, which was trying to get multi-core working. And I'm super scared about the QEMU crash. I think that's still going to happen. I don't really know what to do about that, but I think we can do this though. So I'm going to delete this. Nope, we're not. We can delete this hunk because we don't need that anymore. And now what I need to do is, I kind of hate to do this, But the easiest way is just to copy and paste this code here. If I had time to apply better software engineering to this, it would be really nice to extract this code to a function that can be used here. I even have a to-do saying don't copy and paste this code. And yeah. But whatever. Okay. Okay. I'm going to I think that's pretty much it. Well, okay, so let me just try running this. This should still work. I'm not going to enable multi-core yet. So still running on one CPU, but I'm just going, like, nothing about this really should, like, everything should still work. The only difference is that the user process has a bunch more kernel stacks mapped into it now. Instead of just this single stack 0, it has like stack 1, 2, 3, or whatever, depending on how many processors are on the system. But this should still work, right? Fuck. What? Oh my god, that didn't happen. Ugh. Why is it doing that? That's so disappointing. Oh my gosh. That's so disappointing. Why is it rebooting? I thought I was done with all these stupid reboot issues. Okay. What do I do? I need to debug this somehow. Where is it rebooting? Where could it possibly be rebooting? Let's load icode. I could add some prints. What I'm kind of, do we make it past here? Yeah, we do. Oh, wait a sec. I am wondering. So actually, I'm wondering if I need to cherry pick this commit, this patch in with the I didn't expect to need this to make this work. I'm actually just going to. I don't think I need these anymore, actually. So, I mean, it's pretty easy to try. I'm just going to try to cherry pick. Ooh. Yeah, cherry pick. What? Okay, GCP. Okay. So. I'm just curious, what happens now? It's still, okay, it still crashes. So that did not affect anything. Oh man, so there's something else wrong. Okay, I'm going to drop this commit. Okay. what is going on? So I think, yeah, load iCode. Nope. So I'm just going to debug it. Yup. Okay. Env create. So we know we get there at least. And now what? So now we're at env run. We load in the virtual memory. Okay. So that's where, okay, that was the reboot. That's what happened, I think. Now we're back when we hit the breakpoint again. So it seems like we weirdly, oh wait, I know. I think I know. Okay. It's because okay. That's weird. Let's try it again. The env run. IB del 1. Okay. Continue. Pager, pop, trap frame. We haven't rebooted yet. Okay, so it's not what okay, so now we're in user space. Although, what though? What is this? Lib main, that's, oops. I have no idea. Truly. Okay, do I need to load to 0? Okay, now I got symbols for where I am in the debugging now. I'm apparently in lib main. Ah, I see the mgetID thing. Okay. You main? Nope. Okay. Okay, cut that. So it's crashing in user space. Oh my gosh. Okay. Maybe before I go crazy deep in there, set up VM. Oh, okay. Okay, there's something obvious is that and this has been the stupidest bug that has bit me like probably 8 times at this point, is like not using the correct page end pager. So, okay. I see, okay. That explains some things. Basically, I wasn't actually mapping. I had failed to adjust this. I was accidentally using the old current pagedir thing, and I wasn't using this env pagedir, and so therefore the kernel stack wasn't being mapped at all, which means that when the interrupt happened, the CPU tried to like pointed. What happened when the interrupt happened? Okay, what happened there? So I made a bug where actually this arrow just didn't exist at all. So therefore, when the process made an interrupt and then the CPU points this thing here, and the CPU tries to push some data here, but this is not mapped, and so the CPU triggers like an abort, triple fault, reboots the machine. Right, okay, that makes sense. And now I fixed my dumb mistake. Any other dumb mistakes? And let's try that one more time. Okay, that's what we want to see. So this means it is still totally working, which is good. So that seems to be working. And then, oh, okay. So first thing I'm gonna do is commit some of this. Fix support multi-core by mapping all kernel stacks into env. Distant with mem init mp. Okay, stand up and stretch break. Be right back. Yay, thanks Ismail for the encouragement. Okay. So basically, we get to go way back up the board now. Three. Okay, rewinding basically all the way back to like a long time ago. There were these 2 major crashes. First, it was like the QEMU crash, and then this page fault in kernel mode for div 0. As of right now, we have officially fixed this. This is fixed. It took us like all this time in this kind of insane journey, but we actually fixed that issue completely, which means we get the fun task of like figuring out whatever's going on here with the QEMU crash. I guess let's see if it still happens. So what was the original? So I know so this Lpic init. if I add this back, actually, disable QEMU crash and simply don't use scheduler. Okay. So this is a bit, I don't know, a bit of a moment of truth. Is it gonna crash? Okay, it didn't crash, but it's hanging. But this is familiar. So this now kind of looks like here, right? So oh wait a sec. Okay, commenting out Lpic init fixes it, but then produces this crash. I just fixed that crash. It seems like now we are leaving in the multi-core bring-up code, but then we this thing leads to a hang. And, you know, I'll take a hang over a crash any day. I mean, maybe most days, I don't know. But let's check out, do I have this exchange in there or not? That would be in trap.c. I do have the exchange actually in there. So initially, but QEMU is, I think under these conditions, QEMU used to crash, and now it isn't. I kind of want to zoom back in the history just to verify that. So we did 2 fixes, basically. I'm going to quickly rewind back to here just to check. So here we have the exchange. We have, oh, did it? Yeah. And my recollection was that QEMU would crash. Does it? Yes, QEMU crashed. Okay. So yeah, wait, so this is actually really good news, I think. So under these conditions, QEMU used to crash, meaning these conditions being Lpic init enabled and the exchange present. That used to be enough to cause a crash. But then I changed my code to properly map the stacks and stuff. Yeah, this assertion, this like message is so opaque to me. Some mutex. Anyway, but I changed my code, and yeah, so just to see it one more time. Under those conditions, QEMU would crash every time, and now with the latest state of my code, under the same conditions with the exchange and with the Lpic init, we only see a hang. So I don't know, we're not out of the woods yet, but that is actually a little bit better news. That's not immediately crashing. So now I just need to figure out what happens. Okay. Okay, so saw earlier. It's not hanging, but looks like, okay. QEMU's not crashing. Good news, but it leads to this hang. Yeah, okay, well, let's see what that's all about. What? So there's only one CPU still. Maybe just out of curiosity, what if I cherry pick this commit back? What happens then? Oh, ooh. Now we get the crash back. Yuck. Okay, that's bad news. Okay, that's bad news. I don't know that. So I don't know what's going on. Maybe I have a bug in this commit. That could be possible. Wow. What to do? Okay. When in doubt, I just write down what I know. Okay. Add the TSS stack patch, then the crash. QEMU crash comes back. And I wonder why that is. So what could I do right now? What are my options? I could try to debug the hang. That's one thing I could maybe do. Try to look for bugs in my TSS patch and hope that that's the cause. It might be, I don't know. A lot of this TSS stuff was quite fiddly. I thought I did it right. But maybe not. Okay, what do I do? I would be interested to understand this hang a bit more. So, I still haven't enabled multiple CPUs. CPUs just get set to 1. And we can just see that here with SMP1. So, this patch should still work fine with only one CPU, I think. Or the previous state of the code should still work fine with only one CPU. Yeah, give me 1 second. Yeah. So I don't know if I need to introduce this yet. Is there anything obviously... wait a sec. I actually did have all this multi-core stuff working to some degree weeks ago. I only noticed a bunch of issues once I started to actually try to execute a process. So I feel like this is what that tells me. So I think this code is somewhat solid. Maybe. And there's some other issue that I still haven't fixed it, even with these things. Brainstorming. Let's take a look at this hang. Yeah, let's take a look at this hang. Okay. So I'm going to revert that commit and run this again, and now we observe the hang. Just out of curiosity, what happens if I try multiple CPUs? We still hang. Okay. So we should definitely not be hanging even under one CPU. So let's, I don't know, let's debug it. And end run. Okay, so now we're here at end run. And let's just see what happens. Pop trap frame. Okay. So we page faulted immediately. And now we just hang. What could this be? That's so weird. What? Oh. Okay, let me try that one more time. Wait, so we just page faulted again? We were trying to handle this. All right, give me 1 second. Be right back. Quick. All right. Yeah, wait, so what, so we were handling the trap. And it seems like we page faulted on trying to, we page faulted here. Is it possible that this is like a loop, but where just like it keeps page faulting? Not. I would kind of think that that wouldn't be possible. Like it would triple fault or something after a while. But it very strongly seems like okay. Actually, I think that patch is solid. Multi-core boot up did work before with it. So, okay. So here we go. So, So let's just see it again. Let's just step through here. This CPU test back here, and again, that is so interesting how we can just loop here and not have like a triple fault or something. That is so mysterious. Up in an infinite loop in the trap handler because the trap handler page faults. Why doesn't this trigger a double fault? Is that a triple fault? So that's an interesting question, but it seems like there's some problem with accessing this Lpic ID thing. So that would be interesting to take a further look into. Let's can I break it? See, oops. CPU. Can I do that? Okay. Okay. So it seems like Lpic actually has an address. But that's EF8. That's kind of a, is that a weird? EF8. Oops. Memory, yeah, so this is, which kind of makes sense. It's memory mapped IO. Wait a sec. Okay, I know. Okay, I think I understand this actually. I think it's actually the exact same thing from here. By that I mean, so I fixed this bug by making sure I was consistently setting up the kernel virtual address space in the same way as here. And I think this is another example of an inconsistency in doing that. So I think that's here. I'm actually kind of forgetting. Wait, it's like, what does this do? PMAP 788. Reserve bytes in the MMIO region and map this place. Return size does not have to be multiple. I'm actually pretty confused. Wait, what is this? Preserve bytes. Okay. So we have this specific region called the MMIO region. And I see, okay, so we make various mappings. So we map various chunks of physical address space into there. I see. And you just give it a physical address and how long you want to map into this region, and we just stack it on top, basically. And here, yeah, it's exactly the same thing. Wow, this is getting kind of annoying that it's actually a huge problem that our kernel virtual address space gets so out of consistency with the environment kernel address space. Almost to the point that I get the sense that I'm doing something like really wrong. Initialize for per environment. And the key, yeah, like it's not able to use the Lpic because it's not because the memory is not mapped. I feel like what I need to do is well, so who's calling this anyway? Lpic.c is calling this. Like, I'm kind of getting the sense that I need to add a parameter, but it doesn't make any sense. to yeah, I am still thinking about how to solve this. Wow. So we can access it. So I need to map that into the environments kernel region. Map it. Like, okay, I get the sense that I'm missing like I'm missing some kind of CR3 swap. That's like one reaction. It's like, okay, when I trap back to the kernel, should I be swapping CR3 swapping back into the kernel? But the next, like, the answer is like, well, no, that's like a CR3 swap is a super expensive operation. So you don't want to do that on every interrupt. But it's really cumbersome. Like I'm actually kind of, okay, what's the easiest way to solve this? So I feel like this is not how it works right now, but some notion of like a set of basic page tables that are just like already set up for the environment to use that just get like copied on every new environment will be the way to go. And we like run some code that sets up these base page tables like once and then just copy them later, as opposed to this kind of in-depth, it's like a lot of code that manually sets up the page tables for every, like, yeah, for every process. But okay, whatever. I'm just gonna dig myself deeper into this hole and hack my way out of it. And I think the easiest way to do that that's the craziest thing. So we have these two different things. We have this physical address, and then we have this virtual address, which is just the mapped address of the virtual address, which gets globally saved. So it needs to be the same in all processes. It needs to be mapped to the same address and all mapped to the same physical or no, that this literally that virtual address gets used in so many places, including trap.c, because it's used immediately here. this CPU called CPU num, which uses that virtual address. Okay. Okay, so the question is, how do I map that? How do I make sure that virtual address is available in every process? Wait, sorry, lost. Where do I do that again? And instead of VM, right? So what I could do is I could call boot map region. I guess. Okay, I need to. So the kernel page directory, I kind of don't even understand who's even using. There's this notion of a pure kernel page directory that is not associated with a user space process, and a bunch of stuff gets mapped into it. But then we transition over to running a user space process, which has different mappings. So we kind of replicate that in a copy of the, like a copy for the user space process. We run with this for a long time. Then it has an exception or an interrupt. It traps back into kernel mode, but still running with the user spaces page directory, not with the current page dir. But then, so that happens. But then we're going to access memory addresses that are only mapped in the current page dir, because we haven't replicated that yet. Okay, the easiest, stupidest way to do this, I think, is it's going to be Lpic adder. I don't even know if it's writable. I'm just gonna make it writable anyway, and it's going to point at Lpic and page size. This is like a crazy guess. How is that not? Oh, is it not exposed in a header? Because like, why should it be? But wait a sec, a lot of other people use this thing. Lpic.h? Is there no, wait, what? Our CPU num is in here. But there has to be a Lpic. CPU. Okay, what CPU.h is what? There's the header for a lot of this stuff. Okay. So that's what allows. So it allows others to use these things. and then this probably includes cpu.h. Then I am like weirdly, okay, 20-second stand up and stretch break. I'm weirdly trying to map this at this very specific virtual address, which has already been determined elsewhere in the code, because Lpic init, right? That's the thing that determines this very specific virtual address. This runs pretty early on the main CPU, and it just kind of saves this global variable, which gets used frequently later. I can't, like, I could try to just like expose an argument, but and then call this from the end instead of VM, but that's not exactly what I want, because I want to force it. I need to force it to allocate at a very specific place, but maybe that's fine, because this runs. So this is setting up a totally new address space. But really, this like kernel virtual address space should be absolutely identical to anything we do here, basically. Yeah, it. Can you use current pager as a template? Yes. What does that mean? I wonder what this means. I actually think this is saying don't copy and paste all this junk. Instead, you should be copying data from current pager to populate this. I think that's what it means. So, I think that's what I'm gonna do, actually, because it's just, there's no way this is workable in the long term to manually keep these two, like, pieces of, even if I extracted it out, this is weird. So I think, yeah, we need to use current pager as a template, and like actually, like, not in terms of the code sense, but like really copying the data from current pager. So what would that even mean? I would find it helpful to get back to our diagrams here. So this current page dir has just been set up in memory like perfectly. It's a current page dir and the page tables and stuff. And so currently end page dir. So we allocate a page directory. And then just call all these functions again on it. And these functions, boot map region, it does things like actually allocate page tables if necessary. And so we have this thing that already exists with all these page tables. We created a new page directory and we like manually repopulate it. What would it look like to copy the data? Initial VA below utop. So utop is here, and everything is identical above here, except for something UVPT. Do not need to make any more calls to page alloc. Options in current pmap.h. Is there something I'm missing? I'm not sure what it means by that. Okay. Okay, in order to actually copy the current page dir, I would need to copy it and everything it points to, and probably call page alloc a lot. Maybe that's easy? But it's also saying you don't. Or, okay, maybe I'm overcomplicating it. So to sketch it out a little bit. So I'm gonna have like a page directory. I don't know what the easiest way to do this is, but and it has like all these pointers to different page tables, right? And then I have this new page directory. If I just blindly copy it, it's going to be exactly the same and like replicate all these pointers, I suppose. Maybe that just works. I wonder. And then I'd have a perfect copy of anything that was previously set up with current pagedir. And maybe that's why they didn't inform me to update and set up VM, because I was just doing this totally wrong. The alternative, I think I was jumping to some idea that I needed to make a deep copy of this whole thing. But I am not sure I actually need to, because then, so the current pagedir has a bunch of mappings in it for like the pure kernel stuff. Then the user space shares a bunch of those mappings, but then also has a bunch of other ones for its own unique user space things. So actually, so we start off by copying this thing. We inherit, so get all these pointers, and then we just then we further customize it with this. So yeah, you just need to copy the pointers. I don't need to copy the pointers. I need to just copy the entire data, like the whole data. Like the page directory is an array of page directory entries, and I just need to copy this entire, I can just basically treat this as like a whole buffer, like an array, just literally copy the array. And I it's very rare to do this in C, but I am kind of wondering if it's as simple as this. env pagedir equals current pagedir. But wait, no. Okay, yeah, so these are pointers. So it's not exactly, or is it? Wait a sec. Are you maybe? No, it's not. No. I definitely need a separate page directory. But I think I just, yeah, I think, wait, no, never mind, because this is just a pointer to a single one. So I think I might need to do a mem copy. At least that is, destination would be env pagedir. The source would be current pagedir, and the size page. What's the most idiomatic way to get the size of this whole thing? It's like, I actually, oh, it's just one page, so it's page size. Gosh, I said in the title that I was cooked because I have been debugging these crazy bugs for so long, and I feel quite cooked by them. So that's this is a very extreme change. But now I can just come down here, and comment out all of this. This is crazy. Does this work? Is that like one? Oops. Okay, that's like, I don't know what's gonna happen. Let's just run it. Holy crap. Okay, I'm not totally sure what happened, but like something really worked just now. And that might have been it. Whoa, that's wild. And that might explain it. I mean, because I was earlier in the stream, I was complaining about how the course never told me that I needed to update this function, but it was actually my fault the whole time. I was doing it wrong the whole time by copy and pasting all this setup code. In reality, I just needed to mem copy the existing current page dir. And that's it. Wow. That is incredible. So I think yeah, that's like the most satisfying thing ever. Yeah. Yo, what's up, Yash? Yeah, I remember you DM'd me, I think. Yep. So that's super cool. And I actually kind of forgot even what the code looks like. So I've enabled this thing again. I'm doing this properly. And like, okay, what was happening? Okay, time to go back here. So I'm just going to copy in the diff. I fixed it with this. It was actually something I've been doing wrong for a very, very long time now. An original mistake in my orig VM implementation. Instead of manually replicating all the mapping code, I should just simply copy the current page dir. Yeah. Because env kernel virtual memory didn't have the MMIO region. It was very difficult. It wasn't easy to just add another boot map region call for this, which made me realize I was doing this entirely wrong. And now things seem to be working better. So what did I do to get here? I had this hang, right? I re-enabled it and it hanged because it was infinite looping. So now I've fixed that. So now here's the scariest moment where it's time to see okay, to enable Lpic init. All right, 20 seconds, be right back. Okay, renewal Lpic init. Now that the kernel null dref is fixed, we can slowly work our way back to getting multi-core working and investigate the QEMU crash. I don't know, I'm just gonna add that. Fix. Instead of trying to replicate it manually, this fixes an infinite loop where a user env will a user when this fixes an infinite loop that happens when an env traps. Trap handler tries to use Lpic, which was not mapped into envs. That produces an infinite page fault loop. Unclear why that didn't produce a triple fault. Okay. What's up, Arbit, random user? Yeah, I'm using VS Code. And now for the ultimate moment of truth. Time to undo the revert and see what happens. Is QEMU gonna crash? QEMU is probably gonna still crash. I really just hope it doesn't though. Holy shit, it didn't crash. What? What? Okay, I wasn't expecting that. Wait, so that's huge. To be honest, that's actually massive news. QEMU has been, because yeah, holy crap, because this stream is just massive wins. Thanks, Ismail. Wow. Now that is that true? Wait, I almost kind of don't believe that. Like, but CPU's 2? Is it gonna crash? No. Okay. But wait a sec, what? It says wait. I think it may have happened, but okay, I kind of got myself so confused with all this stuff. I'm kind of just cherry pick. I need to cherry pick more stuff, I think. But I think, yeah, I think that did it. If we check back to this, wait a sec. So here are the fix now. So I removed the revert. So I think if we check back out to this commit, the one right before this like fix, QEMU should crash. Yeah, it crashes. Okay, good. And then I check back to the one with the fix. And it doesn't crash. Holy shit, guys, we did it. That's so satisfying. Oh my gosh. That is huge. Because I was really concerned about the QEMU crash, just like being completely a roadblock that I just would not be able to get past, and I would need to stop learning OS development. But that's actually really satisfying. And now, what I'm just gonna do in the final moments of the stream is cherry pick some of these fixes. So the CPU's thing was actually broken, apparently. Or actually, what's the best way to do this? I guess I'll just do it here. I'll cherry pick this thing. Git cherry pick. No, what am I doing? No, I'm gonna make QEMU CPUs 2. What happens if I try this? Okay. CPU don't. CPU 1 starting. Let me try 8. Yeah, check that out. Crazy. So this is the code that I got working a long time ago, kind of, where it was starting up all the CPUs on the system. But then as soon as I tried to actually execute any kind of process, QEMU would crash. QEMU would crash, the kernel would page fault, the kernel would null pointer reference, all this stuff reared its head. And then over the last, I want to say 4 weeks of this, we've been chipping at this week by week to debug this and understand this. And literally right in this moment, we finally reached a point where I can actually bring back all that code, launch all the CPUs, but not have everything fall apart the moment I try to run anything. So here I'm bringing up all the CPUs and then just doing the most absolute basic test of running a simple user space program that does a divide by 0. The OS handles that and then exits cleanly saying no runnable environments in the system, and then drops into the kernel monitor, which is totally expected. So that's dope. Is there anything else to do at the moment? Yeah, not really. Now I can, there's a ton of Git cleanup work for me to do to clean up all these branches and stuff I made for the debugging. But I can just go ahead. Well, yeah, I don't know if I want to necessarily go into that yet, but the next steps, cherry pick the rest of the commits my debug branch is still missing, e.g. the big kernel lock commits and basic round robin scheduler and whatever this thing is. Do things still work? I'm just gonna take a screenshot of this Lpic screen. Got it working. Apparently fixing all these virtual memory issues etc. fixed the QEMU crash also. Sick. Next steps, cherry pick the rest of the commits and do a big git branch cleanup. Then keep going with lab lab4. Okay. And on that note, I'm going to bring the stream to an end. Thanks so much for watching. I'm going to be away next week, so I have a pre-recorded stream actually for next week, which will show the backstory of this whole thing that I did right before this session, the stag situation. But then I'll be back the week after that. So yeah, thanks Ismail. Thanks for hanging out as always, for anyone watching, feel free to like, comment, and subscribe if you dig the content. I have a Discord server, which I will put in here. Feel free to join the Discord if you want to hang out. Yeah, it was a pleasure, Ismail. Thanks a lot. And I'll see you all in the future. Have a nice Sunday or whenever you're watching. Peace. Bye.